convenient. This is an account of joint work with Alison Pease, who's sitting at the back there. I work at Queen Mary University of London, which is about 2 miles east of here, but I'm currently on sabbatical at Edinburgh. So, the Mathematical Cultures Initiative. I'm just very intrigued by this and intrigued to find see what's going to emerge over the course of the next 3 days. The place I've come from is perhaps a different place from some people. A bit about me. I started out life as an honest-to-God group theorist. I did an undergraduate degree in Cambridge in England, and then I did a PhD at the University of Warwick. The University of Warwick, for people who don't know the UK research maths scene, had and has a very exciting maths department. Tony Gardner and I were just talking about this earlier on. Tony was there right at the start of it in the late 60s. I'm a bit younger than Tony. I was there when it sort of got going a bit further in the late 70s. But we had this amazing initiative in the UK in the late 60s. A lot of new universities were founded, and Warwick chose to specialise in mathematics, and it put together a superb mathematics department. Kristen Zeman, somebody you may have heard of. Tony was reminding me, sort of cajoled, persuaded, bribed the best young mathematicians from all over the world to come and work for him in Warwick and start this radically new and exciting maths department. Of course, one of the reasons it was radically new and exciting was it wasn't hidebound by the traditions of Oxford and Cambridge. It could do things in a new and different way. So I worked as a group theorist, working on things to do with automorphisms of p-groups. Well, never mind what they are. If you do it, it's one of the most incredibly exciting things. If you don't, I only just discovered this morning, thanks to Googling it, that it was number 8 in the top 25 hottest articles in the Journal of Algebra, April to June 2007. It's quite possible the Journal of Algebra only published 9 articles. I don't know, but league tables are everything. That's certainly something that's changed since I started my PhD. But I also, more recently, I moved into computer science in the 1980s when there were no jobs in mathematics in the UK. And I started to work in the field of computer-checked proof. What's that all about? Well, it's the endeavour of getting computers to produce formal proofs, a la Russell and Whitehead. Russell and Whitehead, of course, did not have a computer to check all this. It is Volume 2, page 79 of Principia Mathematica, where we finally learn something useful. We possibly learn that Russell and Whitehead have a sense of humour, but I'll be like actually, the hero, or possibly heroine of this thing must be Russell and Whitehead's typesetter. I mean, they didn't type it, set it themselves, did they? Somebody was sitting there in the bowels of Cambridge, I presume, Cambridge University Press, typesetting stuff. I produced this slide at another meeting, and somebody pointed out to me something I hadn't quite realised before, which was that in the early days of this computer-checked proof malarkey, somebody did start to put into a computer Principia Mathematica, and Russell was still alive. I think this must have been the late 60s, when Russell died. Anyway, it was the late 60s. But apparently Russell was in contact with whoever it was and said, well, you know, nice piece of work, wish we'd been able to do it that way, almost to that effect. But it's one of those things where you suddenly go, gosh, I never thought of that. Well, it would be a whole other lecture, and also interesting, no doubt, from the point of view of mathematical cultures, to talk about where that endeavour has got to. There's been significant investment in it by companies like Intel, because they want to be absolutely certain that their floating point calculations are correct, and these are not the kinds of proofs that anybody is going to want to do, but they don't, you know, all the things that, and yet another discussion you talk about being desirable in mathematics or mathematical proofs don't really necessarily apply to this stuff, which is just big and boring, so very well. But there's also been work in mainstream mathematics, most particularly fly-spec, which is Tom Hale's formalization of the proof of the Kepler projection, which is pretty nearly done. So that's a whole endeavour of mathematical practice, and if you want to know a lot more about it, you can go read the wonderful book by Donald Mackenzie called Mechanising Proof. How did I come to think about mathematical practice? Well, I've been working, as I say, in this sort of area for some time, and I began to realise that although we would like to think that it was having a huge impact on the culture of mathematical research, actually it isn't really. Tom Hales went off and got to grips with this formal proof because he's the kind of person he is, and he really wanted reassurance of this proof of the Kepler conjecture, but most mathematicians don't. Most mathematicians, as will be familiar to you or rehearsed perhaps in other talks at this meeting, most mathematicians don't go down as far as this in trying to do their mathematics for all reasons you might guess. And so I started thinking about mathematical practice because I started thinking about, well, okay, we've got all this stuff. We've invested in the computer science community a lot of time and energy in producing these machines that can do formal proofs. What more would we need to do to actually make it useful, make this stuff useful to mainstream research mathematicians? And so I started thinking from that kind of perspective, I suppose, of, you know, how does research mathematics advance? What is it that research mathematicians do? All the kinds of questions that are very much in the thinking of the mathematical cultures. But then in particular, can computers help? Could a computer be a mathematician? And what's the future of using computers, using the internet in other ways to support mathematics, like crowdsourced maths? So here's a whole other dimension of impact for you. Next slide.
There is a question online too, but you will be coming to this later on. And this is Apple and Hacken's proof, the so-called proof.
Oh, well, look, rather than attempt to answer it, can I suggest you read the relevant chapter of Donald Mackenzie's book?
Okay.
Yeah, I mean, there is a, we could spend all day talking about Apple and Hacken and so on. In the course of my mathematical career, I actually spent 2 years in Urbana-Champaign at the time when they had this wonderful postmark for all colours suffice. Okay, this was a Facebook meme, courtesy of one of my teenage nieces a few weeks ago. What do mathematicians do? Etc., etc. What society thinks I do, what I think I do, what I really do, etc. But what do mathematicians do? What do research mathematicians do? Well, of course, in your dreams, we have Andrew Weil. Let's devote 30 years of our lives to proving Fermat's last theorem, and my goodness, we do. In your manager's dreams, someone mentioned Peter Cameron a little while ago. In your manager's dreams, well, you're a machine that earns money for the university by doing the right things. This is what we don't do, really, as I just said. We have philosophical approaches to what mathematicians do. We have sociological approaches to mathematical practice to mathematicians. Thinking about what mathematicians do. This is as we were hearing at the start, here at the start. This is a kind of interdisciplinary endeavour, thinking about what, and all of this, where I'm coming from, is production of research mathematics without even getting into teaching mathematics or engineering mathematics or cool stuff that turns people onto mathematics like pseudocodes. I had a conversation. I just come back from holiday in Turkey. I speak no Turkish, but nonetheless I was able to bond with a Turkish lady on the plane because we were both doing the pseudocode, and we managed to communicate by sign language that this was a worse addiction than smoking. It was quite amusing. Just a number of perspectives on what mathematicians do. So what the take that I have, the thing that I started thinking about is what we can learn from mathematical practice on the internet. Now, there really is an enormous amount of mathematical activity on the internet of different kinds. I only really discovered quite how much when I had the misfortune to be stuck at home ill for rather a long time. And when you're stuck at home ill, you spend far too much time on the internet. And I realised that you could spend an enormous amount of time on the internet reading about mathematics. And this provides us with an enormous number of sources for mathematical ethnography, sociology, study of mathematical practice, whatever you like to call it. After all, ethnography has practiced. What do you need to practice ethnography properly? Well, you need to find somebody who's motivated enough to spend their energies, their passion for ethnography or sociology when they could be studying any community in the world, doing anything. They have to want to study this strange community of research mathematicians that hang around in math conferences or something. Well, that's quite an ask, really. But now, what do you have? Well, you have these amazing resources which I'm going to tell you about, which allow you to do mathematical ethnography for any thing. So, where do we start? Well, I just want to talk about a few of the resources available. Because one of the things that rather strikes me is that there are endeavours out there called things like web science or computer-supported cooperative work, or all sorts of computer sciencey things, studying how to do things on the internet. The mathematical community has just gone away and done it. They haven't paid much attention to all this stuff. They've just gone away and worked out what works for them. And it's actually really quite impressive when you stop thinking about it. This is the site that I'm sure many of you used. It's the History of Maths site at St Andrews, which actually started before the internet, for those of us old enough to remember the olden days. It started as a hypercard stack. Who's old enough to remember hypercard stacks? Well, a few people are. It started. So this is before the web. There was the idea of hypertext. And this is a wonderful site, still maintained by Ed Robertson and Colin Campbell. These are mathematicians and various other useful things. Quotes of the day. Well, what's a quote of the day? Math Math Reviews. Math Reviews is the American Math Society. Puts that used to be produced as big fat books and now all online, produces reviews of every math paper ever published. One of the things Math Reviews is most useful for is providing you with a definitive BibTeX source for papers. Now, those of us who are practicing mathematicians take these two resources absolutely for granted, but not every discipline has them. Computer science doesn't have anything like this. Other disciplines don't have things like this. Of course, there have been mathematical data sources. The Atlas, based at Birmingham and now Queen Mary, tells you all you ever want to know about finite simple groups, whatever they might be. If you want to, you can have online instruction. You can go to do an online course taught by Keith Devlin at Stanford. Learn how to think the way mathematicians do. A powerful cognitive process developed over thousands of years. He's taking that work. The goal of the course is to help you develop a valuable mental ability, a powerful way of thinking that our ancestors developed, etc., etc. I just found that one yesterday. But another thing that's happened is a number of very senior mathematicians have become very visible and prolific bloggers. This is Tim Gowers. Sir Tim Gowers, mathematician in Cambridge, Fields Medal a few years ago. One of the things he's a very influential blogger. He's been heavily involved in the anti-Elsevier movement. Am I allowed to mention? Probably best not mention. Hello, wars of the London Mathematical Society, debates about mathematical publishing. However, Tim Gowers has been very influential in that. This is a blog post. I thought that pair of blog posts he produced during the last ICM, which I went, last International Congress of Mathematicians. He's blogging about a lecture he's attending, which is meant to be a popular account of the work of somebody who's just been awarded with a Fields Medal. And it take me too far off track to spend a long time talking about this. But what is rather striking about this is that he's live blogging this talk. Here we have Fields medalist Tim Gowers, one of the smartest research mathematicians on the planet. He's sitting there blogging away, and he says, basically, I was following this for about half an hour and then I got lost. And actually, you read this and you think, you know, when I was a young mathematician, I wish somebody told me it was okay to get lost in lectures, and that even really, really clever senior people got lost in lectures. And so the role of this kind of blogging activity in creating a culture, creating a community, I think is quite striking. You know, for good or for bad, but there's something happening here about the fact that individuals aren't just prepared to put themselves on the line like that. You know, I suppose that, I don't know whether that's a universal of mathematical culture, or whether it comes down to particular individuals, you know, happen to be around now blogging a lot, but quite striking. Terry Tao is another eminent mathematician who also blogs a lot. Both of these guys, as far as I can see, particularly Tao, seem to clone himself. The amount they manage to blog while doing everything else they do, and both of them having several small children, you know, it's just sort of, how do they do that? The blogging community is also changing, changing the dynamic of some mathematical discussions quite significantly. Try something that's happened with this when I Zoom. That's better, yes. Some of you may recall in the summer, a couple of years ago, there was a claim by a mathematician who worked at IBM called Dale Dolifeld, who proved that P not equal to MP, which had he proved that, would have been a huge mathematical achievement. Now, what would have happened with this proof in the olden days, pre-internet? Well, he would have written it up, he'd have posted it by mail to a few friends, or he'd have sent it to the referee. A period of mature reflection. Instead, what happened was it got out. He later claimed that far more people had got hold of it than he'd ever intended, and there was immediately a discussion in blog space. The P not equal to NP proof is 1 week old, And after a number of very eminent people, including Jim Lipton, hosts this blog, and thought about it, the conclusion was that, well, the approach, the general approach might have something in it. The too many holes in the approach to presenting, or to do this approach as presented. Called back the paper. And this is a very different change, it's quite a change to the dynamic of mathematical research. Not just famous results like that, but these days, typically, if you produced a result in mathematics, you stick it up on the archive, other people can have a look at it, other people can comment on it. We had a little discussion meeting about aspects of this in Edinburgh in April, and one of the mathematicians there pointed out that actually this has completely changed debates about priority, and also, whether it's a good thing or a bad thing, but it's changed, because people put stuff online, it's out there, no argument about it, and also that people can't really claim to be, it's much less likely that people will be aware of other relevant work in the field. In the olden days, it was sort of nightmare as a grad student. You were slogging away at something for 2 years, and then you'd find somebody else that done the same thing. These days, you're much more sharing of information, or much less likely to find that. This might make you more cautious about, change the dynamic in other ways as well. But that's a big change that the internet has made. For the rest of the talk, there's a whole bunch of issues one can pull out around all these sites. But for the rest of the talk, I want to concentrate on two things that Alison and I particularly looked at from this perspective of finding out about how mathematical stuff is done on the internet, and thinking about how the computer techniques that we have might support that and make it more effective. The first is a site called Math Overflow. Math Overflow is a mathematical question answering system. Basically, well, it's fairly straightforward what it does. You post your question, and then there's a discussion, there are answers, there are ratings, and so on. And the point about this, from the point of view of trying to do ethnography, is here you have vast numbers of mathematical questions and answers sitting there, or vast numbers of mathematical conversations sitting there, which you can analyze. And then the other one is, I closed it. That wasn't very clever, was it? Using everything I've been searching. It's everything I've been searching for. TripAdvisor. Very polymath. Come away. Oh, yeah. And the other thing is polymath. Polymath is an approach to proof organised by Terry Tao. The idea of polymath is that a question is posted on the web and it's solved by people collaborating and discussing on the web, showing all their working, and then coming to an answer. So, to go back to the PowerPoint. What can we learn from these things? Well, let's start with polymath. Polymath can be viewed in the framing of citizen science or collaborative science or crowdsourced science. The idea, as I said, is to organise a number of people to help them produce a proof, mathematical proof collaboratively. Now, nothing new there. I'm sure the things that you were telling us about before lunch were collaborative productions in some way. We don't know how, but they were. Nothing new there. But what particularly is new about this is the way that it's being done. Is that the process is being thought through rather carefully in order to stimulate and encourage collaboration, in order to keep many people involved, and in order to make sure that all the routes, all the different steps in the proof, all the different steps in the conversation are documented. This is one of the significant results that they had. They produced in this way a new proof of the density Hale-Stewart theorem. Note the name of the author, DHJ, density Hale-Stewart. And this is one of the polymath problems that Alison and I decided to look at in a bit more detail. What we did was to take what Terry Tower calls a mini polymath problem, analysing the whole proof of the density Hale-Stewart theorem, which took place over several years, would be a major endeavour, for which we would need a research group. But this was something smaller that we could do in a few weeks. So here's the problem. That's the one I showed you a second ago. Can you read that at the back?
Oh, yes.
Good.
Well, it depends on quality of glasses.
Yes. Well, the idea...
Not so clear in the middle.
Sorry.
Arrow at the front.
How do we zoom on this?
Is it not...
Plus.
Yes.
Sorry, Apple Plus.
Yes.
But right now, I guess you should
Yes,
do
you
it.
go back to the depot line and do Apple Plus perhaps first.
I do Apple Plus.
It doesn't seem to...
Doesn't seem to want to. Oh, anyway, so the problem. There, right. Thank you. Well, what was the problem? It says, supposing you've got a set of points in, find that set of points in the plane. Assume that no 3 points are collinear. Good. I'm not very good at drawing. A windmill is a process that starts with a line going through a single point P. Point B. There's a line. The line rotates clockwise about the pivot P until the first time that the line meets some other point Q. It's Q. So the line's rotated around until it meets Q. This point takes Q as the new pivot, and the line now rotates clockwise about Q until it meets the point of S. And the process continues indefinitely. So it's going around there, it's rotating to Q, and then it's going around there, and it's going around there, etc. Show that we can choose a point P and S and a line going through P such that the resulting windmill uses each point of S as a pivot infinitely many times. So let's say, supposing if you choose the line right and the point right, then it will be an infinite process. Why is it called a windmill problem? Well, because it kind of looks like a windmill. It was only after thinking about this for a little while that I discovered that this Math Olympiad problem had been devised for the International Mathematical Olympiad that took place in the Netherlands by one Jeff Smith.
No, Dan Schwartz. Oh, Jeff Smith devised it. Okay.
Jeff Smith devised it. So he said. So there's the problem, and the idea is to solve it by discussion according to these rules of engagement. All are welcome, no spoilers, not a race, update wiki, meta comments go in the discussion thread, be polite and constructive and make your comments as easy to understand as possible. So, that's an invitation to collaborate. And what happened with this problem? Well, people duly collaborated. There were about 150 comments in 47 minutes. No, 74 minutes. 74 minutes. This of course, depending on what time zone people are in. You know, some people can get a chance to play unless they have to be up at 2 a.m. And then the problem was duly solved. Well, Alison has a whole talk about this in a rather long paper, but I'll just summarise. One of the things we were doing was just looking at the nature of the comments. After all, this is I showed you a flavour just now. There, yes. So you see the kinds of comments. So this is, we've kind of dived in the middle bit, but so Gal has said something or other at this point where the pivot changes, we do something or other. And then Garth says, yeah, now, well, what if we do it this? Maybe that's a simplification. And then Gal has tossed in another idea, and so on.
Say 74 comments, how many different contributors?
150 comments. How many contributors are there?
I think there were a lot of positions, I think that's around 50.
Yeah. So, it's a bit like this. Some people did a lot of work, some people just threw in one or two. And some people, what's quite interesting is and this is even more striking with much bigger problems, is of course different people bring different skills to the party. And so part of the sort of social thing that's going on is you actually want to sort of keep people in the conversation because they might not have much to contribute here, but they might know something else useful further down the page. There's actually a reason for being polite and not burning people off. And you can see the kinds of discussion, you can see the tone of the kind of discussion that's going on. So here, for instance, Jersey has come up with an example. What happens here? I must be missing something here. And Joe says, yeah, you are, you've got something wrong, and so on. So it is very much like the sort of discussion you would have in the pub. You're throwing around ideas, they may or may not be right, so on. And so when we analysed it, one of the things we were looking for was, well, what sort of things are happening in the conversation? Well, a lot of the things are conjecture, what happens if kind of things. About 10% of them are playing with the with concepts of different kinds. And one of the basic concepts is actually, you see, you start off with a line going through a point. And so I drew a point and I drew a line going through it like that. And of course, but a number of people first playing with the problem actually don't draw it like that, they draw a half line. And if you draw a half line, it's a different problem. The answer isn't actually true, the problem is actually true. So some of it's playing around with that. Only 14% of this is actual final proof steps. The kind of thing that would, if you were to write this up a la Principia Mathematica, only 14% of all that stuff would actually be in there at all, because all the rest of it is examples and conversation and so on. 33% is examples, so what happens in this case, what happens in that case. 23% is other. Well, a lot of other is, you might think of it as just sort of miscellaneous chit-chat, but it is sort of social news, nice idea, keep them coming, that kind of thing. They don't spend a lot of time on chit-chat, they power through to get to the answer. A lot of it is a surprising amount of stuff. And since this is the year of Turing, Alison and I amused ourselves by thinking about, well, what do you, and we were thinking about can computers do this stuff. What do you think of, what do you make polymath, taking part in polymath, your Turing test? You see, your Turing test is supposed to be, can a person pass as a machine? I'm sorry, can a machine pass as a person? The other way around. Can a machine pass as a person? Well, what if your test, what if you were having a rather restricted kind of person? Could a machine take part in this polymath discussion and pass as a person? Well, and if you look at what machines are capable of, which would be a whole other graduate course for me, machines can do some of the things that are appearing in this discussion, like coming up with examples, thinking about concepts, automated proofs. But they totally lack many of the other things, and many of the other things that we're seeing in this, like dealing with analogies and diagrams, dealing with misunderstanding and error, developing and comparing alternatives, fleshing out a rough argument, and so on. So there's an awful lot going on in here, which is mathematical practice, is making things happen, but is not captured by our current understanding of machine thinking. Alison knows a lot about Lakatos, and certainly knows a lot more about Lakatos than I do. One of the interesting things we were doing in looking at this was looking, you can sort of ask yourself the question, was Lakatos right? Lakatos, you may remember, produced a rational reconstruction, as we call it, of a mathematical proof, including all the conversation that goes on as the proof happens. And it's, and of course, you can go through these discussions and look for Lakatos moves, if you like, look for the phenomena that Lakatos reports about, the kinds of use of examples and so on that Lakatos reports. And you find a lot of that. You also find Lakatos like things that, as far as we know, Lakatos didn't write about. Well, the other thing we were looking at was math overflow. Lakatos provides you with one conversation, if you like. Polymath provides you with about, I think they've had about 10 or 12 polymaths so far, 10 or 12 conversations. Math overflow provides you with 27,000 mathematical conversations. And we're looking at math overflow again, just to see what happens in these conversations. And what we decided to do in looking at math overflow was restrict to questions on group theory, but rather, so just to say what math overflow is. Those of you who remember the old sci.math. whatever news groups, it's one of those. It's a site that you go to and ask mathematical questions, but it has a number of features that make it more pleasant to use. Not just the fact that it looks prettier, but things to do with rating questions, tagging questions, rating questioners, and so on. Here's a typical question. Don't worry if you don't understand the question, because you can sort of parse it. Which finite non-abelian groups have long chains of subgroups? Well, it's asking for examples of something or other. So here's the question asked by William DeMeo, edited by Frank Ladish. PM, whoever PM might be, has said, have you considered such and such? The person who answers the question says, oh no, I haven't looked at those. I'll go back and have a look at those. And then somebody has produced a more detailed answer, somebody called Derek Holt, who people in the UK pure maths community will know. This is Facebook for mathematicians. Keeps them off the street. And Derek Holt, people who know Derek Holt know he's one of these wonderful people who knows an awful lot about an awful lot. And sure enough, he knows the answer to this. And he's come up with something or other. And Jack Schmidt had says, hey, thanks, that's really neat. So Jack Schmidt actually isn't the person who asked the question originally. Jack Schmidt is somebody else who's just getting rather interested in this. And Jack has said, well, you made a mistake here. Why does Q have to be odd? And Derek said, oh yeah, I guess I have. But, you know, and I chose this example because you see they're being fairly relaxed about this is somebody just typing an answer, typing an idea rather fast. They're being fairly relaxed about mistakes and correcting each other's mistakes and so on. And then William May will say, wow, that's pretty cool. Thank you, that's it. And you'll see the ratings in action. The questions are rated, the answers are rated. There are there's a whole lot of the individuals are rated. So Derek Holt likes asking questions. It's got a hugely high rating. You can get badges for being helpful in different ways. All sorts of things you can do. I thought it would be quite interesting to go away and look at this and see what we could learn from this about mathematical practice. And I cut down the 27,000 questions to 1,377 questions on group theory. Why group theory? Because that's what I did my PhD in, and they're the only questions I actually have a hope of understanding. Looking particularly at what kinds of questions people are asking and what sort of phenomena occur in the answers. Remember, we're trying to think about how do we get computers a bit better at doing mathematics. And because I'm on sabbatical with in Edinburgh, where there is, as was referred to this morning, a rather fine group of sociologists of science, they don't really talk about the science wars anymore, as you said. They're all off looking at synthetic biology, large-scale software infrastructures. I'm trying to be a bit principled and use methods of qualitative analysis, but methods of qualitative analysis also have their own wars if you're a sociologist. But the nice thing about talking to somebody in for a sociologist was they told us how to avoid the wars. Just walk this way all the time. Of course, we're looking at lots of text on a computer, so we could throw all sorts of computery stuff at it, but we haven't yet. So, the idea is to look at the questions and try and come up with a classification of what kinds of questions are being asked. And I had quite a few goes at this, but eventually we sort of fell into we fell into a classification that seemed to work. And these are some of the categories we were using. What's going on? There's quite a lot where somebody just describes a mathematical phenomenon and says, well, I've seen this. I think somebody must have seen this before. What is it? People asking for references. People asking for examples. People straight out asking if something's true. People seeing and so on. And in fact, when you do the classification, the majority of questions are indeed people saying, is such and such true? About a quarter of them are, what is this? Different proof. Different proof is one that quite often turns up in group theory. There's been one massive theorem in group theory, finite group theory, over the past 30 years, which is the classification, a hugely complicated theorem which classifies finite simple groups, classifies all groups of a particular kind. And so you very often get questions along the lines of, well, is there a proof of such and such a result that doesn't require me to use this great big sledgehammer called the classification of finite simple groups? And that's where, those are the kinds of questions where you quite often get answers of the kind that would never be captured in a maths research paper, because there's somebody saying, no, that approach wouldn't work because, or so-and-so tried that, but it didn't work because, you know, you're capturing a lot of knowledge in this thing that would otherwise be sort of. So those are the kinds of questions people were asking. We then started looking at what kinds of things occurred in the answers. We looked at was the question resolved or moved on, and it turned out that in the majority of cases, people ask this question out there, and somebody somewhere has something to say, which doesn't necessarily answer it completely, but adds some of human knowledge on the thing. What kinds of things occur in the answers? Well, very often people are pointing other people at references. And you might say, well, why don't you just use Google then? Well, the answer is these questions aren't really questions like, what is the capital of Poland? They're not really questions that you can use Google on. But they are questions where, you're the world, I'm the world expert in left-handed widgets, and I've got this question, and it turns out that the one person who can answer it is a person who knows about right-handed widgets, but I hadn't realised that. This mechanism is helping me find that. And then there are a number of other things that occur around the going for. So, what did we learn so far? Well, we learned that it's very efficient at what it does. Most of the questions are resolved or moved forward, and even if they're not, they still provide information. Why does it work so well? Well, it's capturing expertise that isn't really in mathematical papers. Your typical mathematical paper starts off with, well, if you're lucky, it's a sort of paragraph of chat, if you're lucky. Then there's a statement of the theorem. Then there's the proof of the theorem. Then there might be a little bit of discussion at the end. But this will be in natural language or in mathematicians. But it won't typically. The style of the presentation of mathematical papers doesn't capture all the byways. It doesn't capture the, I got completely stuck on this, so I did that, and here's this useful example I found along the way. There are a great many other things that the practicing mathematician knows about the problem they were trying to solve that they don't write in the paper. And this captures the stuff that isn't written in the papers. This also finds the expert, and all those mechanisms to do with tags and ratings and so on. You may have seen those sorts of things before. You've seen them on Amazon. You've seen them on eBay. All those technologies invented for other things are actually being used here to just to help this site be a bit more easy to use, but help you find the expert. And well, I suppose this is a bit of a virtuous circle thing, really. You do get participation by the expert. So, this is an opportunity. If you have a sensible question, people will engage. And I do think it's actually quite a remarkable tribute to the mathematics research community that you could be somebody completely unknown from a non-Western country, and if you asked your question in sort of reasonable English and you understood the conventions of the game enough, you could get an answer from a top mathematician, who will treat you with respect. And it is a very civilized and polite community. One can contrast, I don't know if anyone's ever looked at the Foundations of Mathematics email list. Yes. Well, for those who haven't, the words very civilized do not immediately apply to the Foundations of Mathematics email list. It's quite a sharp tone, rather often, An unknown mathematician from an unknown part of the world would be taking their life in their hands if they took part in a discussion on font. They wouldn't on here. And when people do ask questions that are a bit naive, then sometimes people ask questions that are well-intentioned, but to which the answer is basically, it would be a good idea if you went and read a first-year textbook before you try to think about this, and they will get that answer, but politely. But all of this, so it is, I think the mathematics community should actually be quite proud of itself for that sort of, for this aspect of it. I was talking to somebody in chemistry who said, well, she just couldn't imagine something like this happening in chemistry because it's just a lot more competitive, it's a lot more cut and thrust. You wouldn't reveal your questions. You wouldn't sort of give away your knowledge in this way in chemistry. I don't know if that's true, that's just what I'm told by a chemist. So there are all of these things, and all of these things are things that people studying these other, way off things like e-science or internet science or sociology of the internet or something, go and think about it. One can see all these things in this. And then again, when we look at what's occurring in the answers, lots of examples, lots of references of history, quite a bit of clarification of definitions or concepts. And those questions, sort of those kind of what's going on type questions, they are the questions that sometimes you'll ask when you're trying to learn something. You'll read a definition of something, and then you'll think of an example, and you'll say, but how does that definition fit this example? Sometimes these things are actually clarifying Wikipedia entries. And the nature of the answer is then sometimes actually Wikipedia is wrong. People don't have big, long, complicated proofs. They just have lots of Lakatos type moves, lots of chat.
What is a Lakatos type move?
Where can I start? So Lakatosh's book, Proofs and Refutations, he discussed. It's the term I'm using for things like the different notions of the different uses, notions of how you use counterexamples that Lakatosh had. Okay, so it's just a blanket term I'm using for the kinds of things that Lakatosh observed.
They're different things.
Yes, I know.
Okay.
Yeah, that's what I mean. Sorry, there could be a whole, you could write a whole very lengthy paper on the different. There are different, yes, I know, there are different ones. There are different ways of using counterexamples, and I think we spotted all of them. But then we spotted other things that are of that nature, but as far as we know, Lakatosh didn't write down. So, that's another good question. So, lots more to think about. Lots more to think about what computers might do. And from the point of view of this conference, lots more to pick up on from the perspective of mathematical cultures. So you can look at all of this, and one of the questions that Robin Williams, who's a sociologist in Edinburgh, got me thinking about, I was saying, well, wow, isn't this a new and exciting culture? And he said, well, no, actually, maybe the reason that this is working so well is that all mathematicians are doing is they're taking something that works well in the real world, conversations in the coffee room. They know how to do that. They know how to do conversations in the coffee room as an informal mathematical practice, and they've just translated it to the web. And then they sort of picked up on various webby mechanisms like ratings to do it well. They know how to do constructive friendly conversations in the coffee room. They also know how to do good old arguments in the coffee room. And so the good old arguments they put on FOM and constructive friendly conversations they put on here. Is it a new mathematical culture or a different, a manifestation of an old mathematical culture? But the fact that it's there allows us to study it in detail and allows us to allows us to gives us an evidence base for looking at a great many more questions. Okay, thank you.